Good morning. Good morning, everybody. Yeah, let's start as usual that I take you to our web page and just to see where we are and where we're heading. So yeah, last week was Easter. I hope you enjoyed the holidays. So right now we are here. So we are going to do reinforcement learning 1 and then reinforcement learning 2. That's going to be the part on reinforcement learning. And so in 2 weeks' time, there will be a midterm exam. So with reinforcement learning, still the same kind of approach that actually the overlap with the Berkeley class is very big. So basically, we can make very short lectures, but we can, of course, I'm here for your questions, and we can make it interactive. So yeah, so I assume again that you watched this lecture from Berkeley by Dan Klein. And for next week, I will ask you to watch this reinforcement learning 2. It really nicely matches with the content that we have in our curriculum. And then that will basically conclude this whole big block, how we were building up the complexity from search, where we had basically complete knowledge of the problem and no uncertainty, over games, so adversarial search, where we had the opponent, where we could assume the opponent is rational. So there, there was uncertainty on the part of the opponent, but by making this assumption, it was still quite, easily tractable in a way. Then we had these explicit random elements, like games where you are throwing dice. And then we introduced these Markov decision processes where you have uncertainty about the outcomes of your actions. So that was until now. And what changes now with reinforcement learning is that you don't even have the model of the environment. So up till now, we always had the transition probabilities. Either there was no uncertainty or there was an uncertainty that we knew about. So we knew the model of the agent is either you go forward or you go left or you go right with some specific probabilities. And now it's like we are the agent. We need to take the action and we need to observe what happens in terms of both the next state and the reward. So that's basically new. And, it's, of course, again, a more complex problem. And yeah, and so this whole block, including reinforcement learning, will be concluded in that midterm exam in 2 weeks, which will happen here in Brood. It will be, if you look here at the homepage, it will be worth 15 points. And what you can expect is something that basically something practical, something really similar to what you're doing in the labs, like similar to the quizzes. You can expect these kind of questions. There might be few multiple choice questions on the theory, but really where you can score the most points is going to be that you can calculate the things that we were doing in the course, like that you do, you do by hand a couple of, value iteration steps, or, you do alpha beta pruning and, all these things that we did. So you should expect simple practical things that can be calculated by hand, but you need to be able to apply the knowledge. And you don't need to know any formulas by heart. So it's going to be an open book exam in the sense that, you can use your materials, but that doesn't mean that you can, collaborate with others. It should be, of course, your individual thing. And we will then ask you to have, I can tell you more details next week. You will have to have your cameras on during the exam. So maybe next week I'll allow it in Brood that maybe next week we can test during the lecture that you have your cameras on. Okay. So that's the midterm exam. Of course, you have to still keep fulfilling your lab assignments, which is also very important and give you a lot of points. Okay, so I'll switch to my slides, and as I said, we will go quickly because there is really a big overlap with the lecture from UC Berkeley. Okay, so sharing screen and webcam, and here are the slides. this takes us back to the first lecture where we had this whole big picture of the history of cybernetics and AI. And so there is an agent, and it has a goal. It acts via its effector through the environment and gets some sensory values. And here you compute the error, basically what you got from the environment and what you wanted, and that directs your behavior. So that's a very high level picture, but it's also this reinforcement learning that we will be studying now. This is another way of putting it. Yeah, again, agent acts, environment gives you, so this is already more close to the formalization that we will be using. So it gives you a reward back and this next state back. And, and your goal is to choose the action so as to maximize the sum of future rewards. In that sense, it's the same thing that we had in MDPs. However, we have to basically build the model on the run, or yeah, we will see how what the options are. These are some motivation slides, like from Real Robotics that Tomáš Svoboda has there. It's the research from his group, where you have these direct robots, and you have a goal to traverse a difficult environment, and these flippers are those on the robot with tracks. You can watch the video yourself if you're interested. So this is apply this knowledge on. So it's basically from grid worlds to a real situation. We will get a bit closer to that in the next lecture, because so far in the grid worlds we basically can build up tables. We have a discrete world, and we are able to memorize all the knowledge. While of course in reality, if you have real sensors, you're dealing with continuous world, and that has a big dimensionality. And discretizing it and making tables is not going to work anymore. So we will see in the next lecture how we can deal with that, how we can basically approximate the states. Okay, so from offline to online, from offline MDPs to online RL. So why do we say offline? It's because we have the model, so we can basically emulate how the agent is going through the environment, and we explicitly know what the uncertainty on its actions are. So we can basically solve the whole problem offline, basically in our head. Okay. The key difference here that is to reinforcement learning is we don't have neither the transition probabilities nor the reward function. We are somewhere, we know what our actions are that we know, and we just have to keep trying those actions and recording what happens. And that's a much harder problem, obviously. We're still looking for the optimal policy. Yeah. So this is MDP, and this online problem, this is not known, transition model and reward function, and the agent or robot must act and learn from experience. So the idea is you have to do something and learn an approximate model from experiences. And the sort of working assumption that helps us is that even if you have little experience, you have to basically make the assumption, what you know is correct, but you cannot trust it 100%, because you would sort of fall into a local minimum. But basically you accumulate the experiences, and you try to improve the model or the policy as you go. We will deal mostly next week with this exploration versus exploitation. Aha, okay, Rufa, the RL stands for reinforcement learning. Any other questions so far? Okay. And yeah, so this exploration versus exploitation is important here. We will mostly touch on that in the next lecture, but the idea is that you're building the model as you go, but since there is uncertainty, your first or second or third experience are not the very good description of reality. They cannot capture the whole uncertainty in the world. So that's why you have to take this into account, and you should not fix a policy too soon. You have to basically also explore such that you have the opportunity to discover other things. So one possibility is to exploit what we learned, in the previous weeks, and that is, as you go, we will try to learn the model and then use the methods that we know, like value iteration or policy iteration, to come up with the best policy and to estimate the values using what we already know. So there are two components. One is basically a prediction component, which is you want to know, let's say you have a fixed policy and you want to predict what the values would be. And then there is a control component, which is you want to be able to choose the best policy. The two are intertwined. We have seen, how value iteration and policy iteration, it's all basically about expecting, and they are related through the Bellman equations. And yeah, so as I collect experience, I can basically collect more and more and normalize it to get an estimate of the transition probabilities, and the same for the reward function. And then once I have that, I can solve the learned MDP. Of course, I will never completely have that. So basically, as I go, I can try to solve the learned MDP, and I will get a solution that is, of course, the quality of this solution will be dependent on how good the model is that I build up. Basically, it will depend on how much experience the agent already has in the environment. So that's, that's quite straightforward. The reward function in our grid worlds, we assumed there was this living penalty, which was basically everywhere the same. There were only a couple of these exit states. In the real world, it's rarely like that. For example, if you imagine this penalty is for consuming fuel, then if the robot is going up or down or difficult terrain or flat terrain, this will be different everywhere. And so how is this experience collected? It's collected in these observed episodes. So that's training. Exactly that example was covered in the Berkeley lecture, so I will not go through the details. There is a very simple grid environment. Importantly, for basically for this lecture, we will assume, or at least for this first part, we will assume there is a fixed policy. Okay, so somebody tells us what to do. In B, go right. In C, go right. In E, go up. And that's it. These are terminal states that you just exit. And so that means we're now focusing on this prediction problem. Policy is fixed, and we want to know what we can expect if one follows that policy. Okay, choosing that policy will make it more complicated, and we will get to that later. So there are 4 episodes. So that means I always start in, I started 2 times in B and 2 times in E. I always go east because that's my policy. I go C, and then I end up in D. We don't even know if the world is deterministic or not. So if I make these 2 episodes, the same thing happened. So perhaps the world is deterministic, and these are the rewards that I collect. So episode 1, and so I make a table basically where I record these outcomes. Same here. Episode 3, I start here, go north, I end up in C. I go right, I end up in D. And this is the sum of my rewards, -1, -1, +10. Together it will give you +8. Let's have another episode, and same here. Okay, but oops, something unexpected happened here. I wanted to go east. I ended up north. And yeah, I had to then leave through the bad exit. So this is a proof, what you see here, that here you end up in D and here you end up in A, starting from the same state using the same action, that the world is not deterministic according to my experience. Okay, so that's something I can use to build up the the model. Right. Yeah. So then we can ask simple questions like, what would be the probability if you go from D and you go east? If you go from C and you go east, what's the probability that you end up in D? So if you go from C and you go, here's the probability that you end up in D from these probabilities. So how do we solve that? Basically, you have to look up all the instances where there is. Let me underline it here. So you have to look here. Okay, let me. And here. And then how many times you end up in D? You end up in D 3 times. Once you end up somewhere else. So the probability that we're asking, it's going to be, okay, let me connect my tablet. It's going to be 3/4, right? 0.75. So that's fairly simple. And similarly, we could ask what the reward is going to be if I start in C and head east. And this time if I start, yeah. And so we always do state, action, and the next state. So we have this expression S prime, right? So going back, so we have C, east, D. So we are here. We go east and we end up in D. So what is the reward? And I have to basically take this from the experiences. Yeah, so this is the living penalty. This is the final reward. So that would be a -1 + 10, a 9, another 9, another 9. But here it would be a -11. So I have to sum those 4 up and divide by 4. And this is what I get. Wait. No. Okay. Sorry for that. So no. So the one with the A doesn't count because we explicitly asked what the final state is. Okay. So in this case, we do not count that we ended up in A. We just take these 3. This one, and this one. Not this one because it ended up somewhere else, and then it's always the same. And the reward is the instantaneous reward. So in that case, it's just a -1. Okay, sorry for the confusion. What I mentioned previously, that would be the value or the Q value, which we will get to later. So the sum of expected future rewards. Because this is the instantaneous one, right? So this is completely described here. That means you just take one row basically into account. This and this and this. Yeah, and so the difference between 2 approaches that you can take is explained here on if I were to estimate what the ages, let's say in our class are, how old you guys are, then I have basically 2 options. So one is to build up the probabilities. So basically, if we imagine a big group, so let's say if this was a lecture for 1,000 students, then I would ask everybody the age, and then I would simply record the ages, and then I would know the probability that any given student is 20 years old would be how many students are 20 out of those 1,000. And and then the expected age in my class would be that I multiply these probabilities by these actual ages. So if 20% of students are 20, then it would be 0.2 times 20. If I don't know, if 0.18 students are 21, etc. Okay, so this would be basically the model approach. Alternatively, I would get in this case the same result if I just sum up all the ages and then I divide it by the total number of students, and this would be a model-based, model-free approach. I will not build up the probabilities. I will just basically store my samples as examples, basically, and that's it. And yeah, we will see that both approaches can be used to tackle reinforcement learning. And yeah, it turns out the model-free one is easier. It has the disadvantage we cannot use the knowledge that we learned with MDPs, but it has practical advantages, and we will start there. So here we say passive learning. What does that mean? It means the policy is fixed. The reinforcement learning is basically always active, because without acting in the world, you're not going to learn anything because you don't have the model. But there are two variants. One that we call passive, is that the policy is fixed and you're trying it out in the world, but with a fixed policy. And the other variant is active learning, which means you're basically trying out different things as you go. And you may have a strategy, basically, that, how you build the policy as you go, or that you introduce some randomness, which we will see later. So there's a fixed policy. You want to know how good it is. So that's basically like a policy evaluation that we saw in MDPs. Yeah, the difference being that this R and P, so basically the reward function and the transition probabilities are not known. So you execute a policy, you learn on the way, and the goal being learn the values of states given this policy pi. This is the grid world we have seen many times. And yeah, so here is the expected value. So this is the discounted sum of future rewards. We have seen this. Many times. This symbol G, that's the sum of rewards of an episode. We have also seen this before. That means so yeah, that corresponds to one particular episode, the G. Okay. Because yeah, episodes are basically the experience here, so we have to rely on the episodes. So you act according to a policy. When you visit a state, you remember what the sum of discounted rewards turned out to be. So that means I'm acting and I'm making notes. When I reach the terminal state, I go back to all states where I've been, and I update the values. So I basically have the return of the episode, and I go back to the states that were, let's say I end up here. I was incurring these living penalties as I went, maybe minus 0.04 everywhere, and suddenly I'm here. I get a +1 that ends my episode, and now I go back basically to my log, to my buffer, and I update using the the GT here, plus taking into account how many living penalties were incurred on the run. I update the values based on my experience in that episode. And expected value means that as I collect more episodes, I will basically make an average. So each trial provides basically a sample of this V pi, and every episode is basically adding one sample. So yeah, that's I think straightforward. This is one notation how you can write out the episodes. So what does that mean? That means I'm starting always in 1, 1 in this case. That was the starting state in discrete world. And I follow this policy. The arrows here describe the policy. So the policy tells me always go up. But, remember, this is the policy. It doesn't mean you always end up here. So here you do, but here you don't, because of indeterminism. Every step costs you minus 0.04. And this is the next state where you get. So episode 1, episode 2. Okay, sorry. Episode 1, episode 2, episode 3. Episode 3. And if you sum up the rewards as you go, this is going to be your G for that episode. So this is going to be G1 is going to be this plus this plus this plus this plus this plus this. Okay. And yeah, so for example, G3 is going to be minus 0.04 times 4 minus 1. And so this is a method that is called direct evaluation from episodes. So basically I'm doing that. I always do a training episode. I log what happens as I go. Once the episode is finished, I go back and I update the estimates for every state. It can happen that the state is there 2 times. So that's fine. So basically I will have to break it up and take basically one episode from here to here and count it as the, so in this case, the G, or the value of 1, 3 in this case is going to be 1, 2, 3 times minus 0.4 plus 1. Okay, so that's going to be this part. And but since it was multiple times there, I will have to also update it with another value, which is going to involve summing up over this whole range. Okay, so this can easily happen. So I will simply have basically one episode with probably with 2 samples for estimating the value of the state 1, 3. Does it make sense? Is it clear? Okay, good. Wonderful. Yeah, so this can be easily calculated. So V32. Okay, let's have a look what this was. 3.2 is this one. So I will have to first locate it in the episode. So I look through the first one. I don't see it. Okay, here is one. And here is another one. Okay. So let's count for this one. It's going to be minus 0.04, minus 0.04, plus 1, giving me 0.92. Here it's going to be minus 0.04, minus 1, giving me minus 1.01. And the value would be the average return, which is simply going to be the average. So we visited once in the second, once in the third is it anywhere else? Did I overlook it somewhere? Probably not. Right. And yeah, so you simply take the average, which is going to be 0.92 minus 1.04 divided by 2, and giving you minus 0.06. So yeah, that's a very, very straightforward and simple. Yeah, so this, so like this, basically you can do it for every state. You just basically do averages, and that's it. So very, very simple. Here is the algorithm. So remember, there's a fixed policy. You initialize the values arbitrarily. That's like in what we've been doing previously, like in value iterations. A good choice is just make them zeros. And then there is the loop for every episode. This gives you the sequence of states: actions, reward, state, action, reward. This is the return of the episode. So you loop, and then you update basically the value of every state as an average, as you go. So very straightforward. So the good thing is simple, and you don't need any transition probabilities. And you don't even need the reward function. You're just you're just averaging your experience. So that's very, very straightforward. The bad is that each state, for every state, the value is learned in isolation, which is of course not, in reality, that's not true, right? So in the lecture from Berkeley, let me see if I can get so if you actually apply this and these very episodes here, and you calculate the values, you're going to get -2, +4, +10, and +8. And that's what you get from the episodes. But clearly there's something strange here, right? Because so this has a negative sort of expectation. Rufat. Okay, I'll get back. I'll get back to it once I get back to the. Once I finish on this slide. Right. So from this episode you can get these numbers, and so this seems that here there is something negative, but here there is something positive, and here is something very positive. There seems to be like an inconsistency, right? Because if I go right from here, I cannot end up anywhere else. And here I expect a +8, while here only a +4, but here a negative -2. I cannot end up also. So from here and here, I always end up in C, but my expectations are different. And the problem is that basically I was biased by the whole episode, but for some reason I had bad luck, and once going from here, I ended up here. And this is why I see this here. However, this is clearly inconsistent, right? So basically, taking the relations between the neighboring states, like we did, that was the basics, basically, of the Bellman equations. That the states, that are successors or neighbors in the state space, successors in the tree, their values are obviously related. They are just related that it's the living penalty and then the value of the next state. So this is a problem, and that's a problem that the direct evaluation is ignoring, right? And so that means it's sort of counting the episode independently. It's not efficient and it's not in this case, it's basically it's wasting the information that you have to make this consistent, because you clearly know that they are related, the values of the neighboring states. So that's the bad. Rufat questions was the average. How do I take the average for the V of 3, 2, which was here? No. Wait, so I have to go to here. So what is not clear? So I take this one. I take this one. Okay, and wait. I see what you mean. So wait, maybe it's just arithmetics. So we have we have plus 0.92 minus 1.04, which is no, this is correct, right? So this gives me minus 0.12 overall divided by 2 minus 0.06. Why is 1 minute just twice? I think I didn't get why is it 1 minus 0 from just twice? Well, because it's from are we taking rewards from the goal state? So one episode is, so we're interested in state 3.2, right? So what you have to do, you just look through the training episodes, you locate that state. One is here. From then on, you calculate the sum of the rewards, minus 0.04, minus 0.04, plus 1. So your episode has a return from the perspective of this state of 0.92. Okay? And same here. We're taking all the rewards from the state that we're looking at. So that we're interested in the value of this state up until the end of the episode. So the sum of rewards from this state in the episode till the end. Exactly. Yes, that is correct. Plus, there is the additional complication that state may happen, may occur multiple times in a given episode. In that case, you just pretend, as we saw before, once you sum over this part, and another time you sum over this part. You just pretend that they are two different things. Okay. Okay, good. So let's move on. Yeah, so this is what we explained, that state values are not independent. So it's still always the Bellman equations, that basically the key observation that the value of one state is related to the values of the states where you can get from the of the successor states. So far we were interested only in the values, and for a given policy. Okay, so we came across policy evaluation in MDPs, and this was basically this. Usually, it's this one. So this was basically what we used. the problem is that the formula we used, was again using the transition probabilities and the rewards, which is something that is not available. So what we could do is we could use the samples we have for evaluating given policy. So we could, have a trial 1, have a trial 2, and then just make an average. So in this case, we're not using the direct evaluation. We're not doing the whole episode. We're just doing this instantaneous reward plus the value of the successor state. So we're trying to use the Bellman updates, but rather than using the model, which we don't have, we're using the samples. Okay, so for value of my state, I will make an action. I will do take the instantaneous reward plus my current estimate of the value of the successor state. So that's something that could replace the model empirically. That would seem like a possibility. Depending on the environment, in practice, there is a problem, which is that the environment may not allow for this. It may not allow you to. In this case, you're always starting from the same state and you're trying different things, which in some environments it may work, but in some, like if you have a robot, let's say it's a car, and there is some kind of pit. So you take this action, but you fall down here, and you cannot go back, right? Because your car just cannot climb stairs. So you cannot basically infinitely, or as much as you would like to, you cannot just keep trying and then updating the samples. But you have to basically, it can happen that it's not reversible. You cannot go back, and you have to log that experience, but you cannot just try there. So that's a complicated. And so the one important algorithm or idea that is basically key for reinforcement learning is temporal difference value learning. So what does that mean? For now, we assume gamma is 1. That means no discounting on future rewards. So we basically, the key thing is that we will basically update as we go as follows. So from first trial episode, we get this V of 2,3, which is here, is 0.92. Yeah, we saw that before. V1,3 is here. This is the case that we discussed. It's basically summing up this part and then summing up this part and taking an average of the two. So for the first episode, we have no estimates. So we just basically we basically have to use the direct evaluation because we have no estimates, right? And but in the second episode, you already have estimates. So you're going from 1,3, which is here, to 2,3. So we're here, okay, in the second episode. And we have this penalty minus 0.04. So we have the current, so the reward is minus 0.04 plus the estimate we had from before, and this gives us 0.88. However, here we had 0. So this is something we expected. We expected 0.84. But now, if we actually do this step and then use an estimate of the value of the neighbor, so this should be consistent, right? But it's not consistent. So that means that now that we see the new evidence, maybe the estimate based on a single episode was not correct. And so the difference between these two is something we can operate on, and that's what is called temporal difference basically value learning. You're taking advantage basically locally in a given time of what was your current estimate and what happened if you just did this one step, so one, and using the difference to update the estimate you have. So that's the key idea. You update that as we go. And so how do we update? So basically we use some learning rate. In the Berkeley lectures, they often use 0.5, but that's a huge learning rate. So that means you're basically giving half of the weight to what you have just seen. So this is what your previous, so you want to update your estimate of the value for the state. And you make it equal to the current estimate plus this discrepancy you have when you execute this one step and then use the estimates of your of the successors. So this is the and this is for demonstration. You know, this will basically show you what happens, but in practice this would basically be really giving too much value to just the single step that you have just seen. So in practice, you would want to go for something much lower, so something like 0.1 or even lower. But the principle is clear. So basically you have an accumulated estimate and you make this one step and you use the difference to update your estimate, and which is very simple, but actually given some reasonable assumptions, then it's proved to actually work optimally. The assumptions being that all states get updated, and that you basically that the learning rate is within some bounds. You may have some schedule how you want to decrease the learning rate over time, but under basically some basic assumptions, it will work optimally. So that's here. So there is an alpha times new sample, with some weight, and there is 1 minus alpha times the old estimate. Mathematically, what you're doing here, it's an exponential moving average. The recent values, they have basically exponentially more weight, and the old values are basically exponentially discounted. Right. Again, I think I will for the details. I think we don't need to replicate the lecture from Berkeley, and we can check the algorithm though. So fixed policy. Remember, we're still with fixed policy, and we're evaluating that policy. This is an episode. So basically that's our learning experience. That's our training data. And here is this key update term that is, the essence of temporal difference learning. So again, the good and the bad. It's model-free value learning by mimicking the Bellman update. The bad is that if in the end, we want to extract the policy. So remember with MDPs, we had this policy extraction. So how is this gonna work here? So this is a problem, right? Because again, we don't have all the things that we need to do this argmax and choose the best action. So the way out is basically something that we've already seen with MDPs, that the Q values are a very convenient thing. That basically, always you had a square, and instead of having like one number, which is the value of that square, you had it like this with 4 different numbers, one of them, the best one being the actual value, and then you would be the other ones. You would have the other ones which correspond to the value you can expect that when you take a specific action from that state. And that's a convenient thing, and that's what is also going to be exploited in these reinforcement learning algorithms that you will basically work on the queue states. Okay, so we move to active reinforcement learning. So active, again, meaning that that you can choose your actions. You don't have to have fixed policy, and you just try and observe what happens. You can choose. So these are this is still the Q values in this sense are more useful, are more practical. What you see here is that the max operator is shifted. So here you're maxing basically over the actions here, and these are the expectations. But in this case, when you deal with Q values, the max operator is basically taken inwards, and that's in this case convenient, because you can directly max over the Q values that you have, and that's in particular relevant here where you don't have all the quantities needed. Yeah, you can draw this expecting max 3, and it's also in the lecture from Berkeley. So, and this leads us to an algorithm that is a famous one, it's really one of the basic reinforcement learning algorithms, and it's called Q learning, because it's using because it's relying on the Q values. And you learn those Q values as the robot goes, via temporal difference. So you drive the robot and fetch rewards. We know the old estimates, just like for the values here for the Q values. And here a new sample, a trial, and same like for the values, but this time for the Q values, it's the reward plus here it's the, if there is a discount, and a max over the Q values. So maxing over Q values, if you have them, is easy. But the key thing being here that, is as you work on Q values, you keep track of what the best action is in every state. So it's easy. So it's the same logic like with temporal difference learning. You just, instead of on values, you work on Q values. But that is practical, and it's important for the algorithm. Right. Yeah. Yeah. Algorithm. Yeah. Same like for the values, but instead of the you basically put the you put the Q values. Now, this is already sort of gives you an idea what also the next lecture will be about. And these Q functions need to be represented somehow. And the key question is going to be how to choose the action. So we are now with this active learning, so we can, and that's going to lead us to this famous exploration versus exploitation dilemma that we will deal with in the next lecture. So for our grid worlds, we are fine with the tables. But as you can imagine, with the robots, it's going to be a different thing, and this needs to be approximated somehow. which we will look at in the next lecture. And as you may be aware of, there is also the deep reinforcement learning, and this is all about basically approximating some of the quantities, using function approximation, these deep networks are very good at that. So this can allow you to basically handle real world problems and have very good approximations. You cannot basically handle real world problems or even complicated games with having tables that store all these quantities that we need for our algorithm to operate. Motivation regarding the exploration versus exploitation. So shall I drive to the known road or try a new one? Go to the university mensa or try a restaurant? Use the operating system I know or try a new one? And these are naturally we're confronted with these kind of decisions all the time, and the brain has some means how to how to do that, and that also evolves basically with age. Babies basically turn to be more how shall I say? So basically, these kind of model-based and sophisticated approaches, you only learn them in adolescence, and when you're an adult. Babies are basically more greedy, so they pay more attention to very recent rewards, and they cannot fully appreciate that there is the uncertainty, and that it may be better to do something that grants more reward in the farther future. Yeah, go to business or study it. So these are some maybe dilemmas that you guys may be facing. So how to explore? So this greedy is, it's always a component of the algorithms, and that's the exploitation part, because, you cannot explore forever. You have to also exploit the knowledge that you have. So you can, of course, explore randomly with some epsilon. So let's say, it depends on the settings. Let's say 90% of the time you exploit, and 10% of the time you just do a random thing. And that's a possibility. Otherwise, you use a policy. That seems like a reasonable starting point. Problem with randomness, it keeps exploring forever. This is, of course, the many learning algorithms, they have this schedule that the learning rate, this would be time, this would be your learning rate, that it would typically go down. It may go down linearly, it may go down exponentially. And it's usually good idea to have this schedule, how you basically cool down the system. You reduce the learning rate over time, and then eventually that allows you to converge. It may be a good idea to not to have it the same everywhere, but depending on the properties of there are many heuristics that you can basically that you can apply, just like in all the problems that we've seen. So there might be states that are critical, and there it's more important to explore, or that there might be states that you have less experience with. So they were present on fewer episodes, while some of them, they seem that they have already converged, because you have a lot of experience, which seems quite stable, so little uncertainty. Maybe the value there is not good. So so if something is, you have a lot of experience with, and the values are not good, then why you should not try that very often. But some regions of the state space might be promising, and that's where you should focus your attention at. And so this is the end. So this is the lecture that you were watching. These are the two textbooks. Let me maybe, so before you have questions to the slides. I want to also show you something else a little bit, and also this book, because this is going to be the key book for now. Actions, yes. We always, we always know the actions available to us. Yes, Tejas, yeah. So we know that the robot can go there, or depends, of course, whether it's motor speed or whatever. But yes, actions, yes. We don't know the transitions here, the probabilities, and the reward function, but we always know the actions available. Yes. Okay. How will we know if we have explored all the states during each? Question by Ali is, since we don't have the map, how would we know if we have explored all the states during each run? So we don't know that now. We will not know that, and yeah, we have to basically deal with that. I mean, so one assumption here is that so we're mapping directly from the percepts to the states, right? So imagine you have sensors, and then you basically map it onto a certain state, and we assume that that actually works perfectly. So if I'm again in the same state, I can recognize, which in reality is not an easy thing to do. That would be a further complication, but that's for now, that is granted. And so if depending, of course, how much we explore, and depending on the uncertainty on the action, it may take a long time until you discover some corners of the environment, for example, that are hard to get to. But that's reality. So we will never know for sure. But probabilistically speaking, if we do enough exploration, we have in the limit confidence that we have explored all the relevant paths. Okay. Division for the upcoming assignment. Some demonstration. Well, I don't have it ready now. I think that in the Berkeley lecture there's these demonstrations with the different grid worlds, and I'll ask you to watch it there, or you can also ask Philip if he has something ready from the world that you will be dealing with in the assignment. Of course, you have to then, as you see the grid world, you see the map in front of you if the world is given to you, but you have to sort of shift the perspective, because the agent doesn't have this knowledge, right? So even if you see the grid world in front of you, and then keep in mind that the agent doesn't see it like that. It only has the episodes that it went through.
Okay, thank you. Well, the point is that I'm struggling with the bigger maps. I tried the homework, and I think that when I'm doing small map, it's fine. But when I go big, then the agent is doing something random, and I'm not sure if it's correct or not, because the exploration is just weird, and I don't know how it should look like.
Okay, I see. Yeah, I'm not familiar, like from the top of my head, with the details of the assignment. So I'll ask you to check it with Philip during the labs, if I may, Lukáši.
Yeah, sure.
Yeah?
Okay,
yeah?
Thank you.
Okay, thanks. Okay, let me just show you something else now. I stop the slides and show you my screen again. And so one thing that I wanted to show you, there is this OpenAI gym. So it's not that we ask you to work with it, but it's something that is very big in the machine learning community. So basically there are these standard environments provided, and many people, so there are Atari games, there are these kind of environments. There are control from control, basically control tasks. And yeah, so these are standard environments, and the whole community is basically competing. So there are benchmarks, and they are competing with different algorithms. And this is really a hot topic that is a lot of people are trying their luck with their algorithms there. And so one other thing that I wanted to show you is that there is this NVIDIA conference, and it's actually happening today, tomorrow, and on Wednesday. And because it's US time, so basically for us, it's either afternoons or evenings. And these are really a lot of the gurus of deep learning, for example. So for example, there is Joshua Bengio, Geoffrey Hinton, and Yann LeCun, who received the Turing Award basically for their contributions to neural networks and deep learning. And this is really like as you know, a major driving force now of machine learning. Jürgen Schmidhuber is another famous researcher in these areas. So he's going to talk about this. He's going to give an overview of modern AI. So I think this is going to be interesting, and this could also be relevant for us, representation learning for autonomous robots. So there's no lecture that would be specifically about reinforcement learning, or at least I didn't find one. But these are really they are top speakers, and I think it could give you a really nice overview of state of the art in the field. You just go to these pages. You have to register, but it's for free. And yeah, I invite you to watch some of the lectures in the evenings, or afternoons, if you have capacity. I think it's really a unique event that you can learn a lot there. Share the link. Well, I can type it in the chat here. Maybe that's gonna work. And I think it should be very easy to Google, because it's quite a big event. So yeah, I will myself try to watch at least these gurus, because I think it's really worthwhile to hear what they currently think. Anything from your side? So next week, please try to log in with the cameras, and we make a sort of test for the midterm exam, where we would like to have your cameras on. Okay, so next time, please log in with the microphone and the camera, and we will test that everything works. Anything else? Coding. Well, okay. Question is, will there be any coding questions for the midterm, or just theory? So not coding in the sense that you will code in Python, but as I said, it won't be theory in a sense that we would ask you a lot of theoretical questions. It will be questions that you should basically solve on paper, just like what you're doing in the computer labs, like the quizzes. So that's a sort of typical thing you can expect. You can also go through the past quizzes. We will basically, as I said in the beginning, ask you to do alpha beta pruning of a simple tree, or compute a couple of iterations or value iteration, or these kind of things you can expect that you have been exposed to during the computer labs, or also some of the worked examples during the lectures. So let's say applied theory, you don't need to memorize formulas. They will be given to you, or it will be basically an open book exam, but you have to be able to apply the knowledge. So you have to be able to apply it to problems that you can solve by hand on paper. Anything else? No? Okay, so if that is not the case, then I thank you for your attention, and I see you next week.
Thank you. Goodbye.
Okay, thanks. Bye-bye.